Okay, so hi everyone. I hope you can see the screen. So I am Shreyash Pawar. I'm Shreyash. I'm currently working as a data scientist at a startup called Sravati.ai. And this presentation is like a kind of culmination of all the problems which I have faced at my company, where kind of you have to optimize your ML inference. Like normally, when you do ML inference, there is not much overhead as compared to deep learning. But what if you want to do much further computation on based on that ML inference? Like you want to do a lot many combinations of the output that would run into millions and billions. So I saw that there's not a like a ready-made solution available for that. So I thought of making presentation on that, on what methods that I used. So here we go. So the contents for today is introduction to why is ML inference is needed to be good and fast, and what are the bottlenecks. Then we'll discuss regarding parallelization Python. So all the ML inference that we're trying to do is in Python. Scikit-learn and all the APIs are in Python. So you should definitely know how can you increase your speed in Python itself. That would in turn increase your definitely ML inference. And so there are some very famous techniques used for that called as multi-threading, multi-processing. And then we move on to a new kind of implementation for this speeding of your Python is something called as Numba. And then finally, we take a look at few examples for Rapids AI. So Rapids AI is a framework for accelerating your data pre-processing task on GPU mostly, and it is mostly used in training time, not much in test time. So here we'll focus mostly on the test time. So Rapids AI will be a very small part of the presentation if you're coming for that. Rest of the stuff, maximally like 75% would be till Numba. So this is the content. So let's get started. Yeah. So why we are dealing with parallelism itself? So because first thing is, if you look at the clock speed of the processor which come nowadays than like 2 years ago, it has just increased from like 2.8 gigahertz to mostly like 3.6 gigahertz. That too, and like it is overclocked. Otherwise, you normally run at very like at the same speed as earlier. So and that speed is important because that defines your execution time per instruction. Like in Python or any code, every line that you do is one instruction to the compiler, and how many instructions can the CPU do in a second is what that speed is. And because we are not constrained. Now this is all for CPU. I'm not talking about GPU here at all. Our today's talk will be entirely for CPU because ML, I mean, to put on GPU will be a much difficult task than put on CPU. So yeah, for CPUs, also one instruction is we have to compile, that is the number of hertz that we get. And so the challenge with us is whatever the speed we are given, we try to optimize around it. So if we are given for 3.2 gigahertz, can we utilize 3.2 gigahertz like 40 times, 20 times per cycle? And this is, I guess, very important for AI because you definitely we deal with very large amounts of data, and the calculations we do any like even when you do prediction internally, there's a lot of calculation happening to get that algorithm, and those are very bound on CPU. I mean, they are very intensive calculations for any CPU stuff. So hence it is important to know. So to introduce parallelizations, let's look at the example of, for example, your browser. So your browser, so any code has, I mean, your any application has a process and a thread. So for example, so a process and a thread is the smallest kind of unit that you are using to work with. Okay, so for example, if you so a thread is, we could say, a component of process which can run parallelly. It kind of shares the same space of memory and it has very less overhead. So any small thing like you want to play a song, skip a song, that play pause is happening, and maybe if you want to load another song on the side preloaded, that is happening on a different thread. And what is the process? It's like if you have multiple process which are kind of independent of each other, like every tab is independent of each other, that you call it as kind of a process. So here we introduce, that's why the people use something called as multi-threading. So as we saw, that thread is a component of process which can run parallelly. And one good thing about thread is the objects are shared, which can be like good or bad thing we'll see later. So the objects and the space of memory is shared between objects in multi-threading. And so since we said that in that their objects are shared between them, so what if you want to execute a different operation on that same object in a different thread? That would cause a lot of issues. So that's why Python in itself had introduced this something called as global GIL, called as global interpreter lock, where you can't use your object multiple times in different threads. So this was like just how Python was made. Why is it Python is easier to use? Because of this one thing. On a one thread, it's very easy to use, but if you want to do on multiple thread, it's quite difficult because you have to take care of all the operations. And when you try to do multi-threading without like actually keeping the lock fixed, then your code might run even slower. We'll see that how and what the code. So that is an issue with the multi-threading. Coming on to multi-processing, multi-processing process is what where every program has its own space of memory and data to store the instructions. So every process will have multiple threads within it to do its job itself, and we can run such various processes on various other things, on various other maybe devices or clusters. So multi-threading is definitely more lightweight because the memory resources are shared by the threads, and since they share, the same pool of memory, it's kind of very convenient for NumPy and such kind of codes where you deal with a lot of numbers, NumPy and SciPy. So it's kind of mainly used there. And on the other hand, definitely multiprocessing is more flexible, can be distributed across clusters. So mainly, one clear distinction is if your program is, suppose you're trying to do, for example, you want to scrape the web. There you have a lot of inputs and outputs. You have to scrape for one patent, wait for sometimes, go for the next patent. There you can try to use multi-threading because your individual threads are not dependent on each other mostly, and thread is input heavy. Like you're waiting for input and output. Without that, you cannot move forward. So that is a big bottleneck. So that time mostly people prefer using multi-threading. Second use case is if your task is very CPU heavy, like you have to do a lot of computations and your objects are being shared a lot between every computations, then that time multi-processing is very much preferred because that would distribute your load on various cores in your CPU. So and basically, and one more thing is to start a multi-processing has a lot of overheads, but because we have to, for every process, we have to create its own different space in the memory. You have to allocate its create its bytecode again. So it's more heavy to spin up. So that's one more thing. So apart from all of this, we discussed multi-threading, multi-processing. They only speed up to a certain extent. Now to go beyond that, there was something introduced in 2016, a project called as Numba. So this Numba is like mainly we know from earlier that Pythonic languages are mainly called as are like languages that are that do compilation on time, like they are that do execution line by line. That means they're not compiled. So what Numba tried to do was, what if you could take every individual function within a Python and try to compile it and then execute it. So if you see the difference with respect to a language called as C versus Python, so with C, there are two steps to run any code. First, you write the code, and then you compile it. You get a object, and then you run that object. That is, after compiling, you run it. Same thing. It has been kind of copied in Numba, where instead of two steps, everything is done within a single step, where the code where Numba compiles your functions at runtime, which is why they call it just runtime, and then run it. So that's why it is kind of highly fast and good. So and mostly since Numba was started, and since in C, as you see, your types of data are mostly fixed, either it will float, array, or even if you have to pre-allocate, you always use malloc or something like that. In Python, you have list. So mostly it's not for list as such. It's mostly for your string and immutable data, where the length of data is fixed, so that the compilation happens smoothly. So moving forward now, one thing is this all multi-threading and parallelism we discussed, but it's like, why, when is it really worth it? So, I mean, it's only great to start working on parallelism of your code if obviously first your code works, and post your code works, we should first start with the testing. Like, you could write your unit test using PyTest and all, and then it's might be much better to put your time into documentation. Then finally, if you have made your packages easy to install, like you have made distutils setup.py, and then post that, you should worry about parallelism in this case, and that is also even if required. Otherwise, most of the stuff is for Python will get done by just one core CPU and one thread. And one more thing is, great to know that when like Numba won't help you. So Numba won't help you like when you want to compile your complete code, not just a function. And secondly, what if you want to run it using C, like convert your Python to C and C++? That time, mostly people use Python and not go with Numba, because that is more involved and a bit faster implementation than Numba itself. And what if like your algorithms are not numeric as such? So you are using a lot of characters and data, like in touch of NLP, where the data mostly is not numeric. So that time maybe using Numba will slow it down. So it's not good for them. So this is important to keep in mind. So let's look at, to understand how Numba works. Let's look at how your normal Python has been working till now. So your normal Python, obviously we discussed that it runs as something called as using interpreted version of the code. So normally any code has two steps. Like normally codes are divided into two steps. One is compilation and then interpretation. But there's a common myth that Python does not compile. It does use compiler. It uses both. So compiler's job is to compile your code directly into machine code. But Python converts, instead of machine code, to something called as bytecode before, and that bytecode is executing using PVM. So there's a Python virtual machine, and this is all this part of the Python, this model of yeah. So all this all part of Python. So now this has been like how normally Python flows. Now to optimize this, what Numba did was maybe if you could introduce a layer between bytecode and the PVM itself. Yeah, so if you could like directly introduce a layer between Python and Numba itself, where so first what we do is it translates your Python object. So whatever function you use Numba on, it will do something called as unboxing on that. It will get your bytecode, and within your functions, it will see all the types, all the data types of values that you have used, and convert them into something called as type inference. So like if it knows that you're using int 64 and float 32, it will compile them to use it quite faster next time. And and obviously if you have Numba, so it will, if you have NumPy used, so it will directly fetch your NumPy arrays and convert them in for faster inference. So and then it will convert that code into a lower form of code, and it will put it on LLVM compiler. So LLVM is a very famous compiler, has been used in many tasks in almost all the codes in all the systems. So Numba has inherently has LLVM installed at a lower level in it. So when you do pip install Numba, it will also install LLVM on the backend with it. So and it will put that code on the LLVM, and LLVM will execute that as your machine code. So yeah, so this is how your like Numba internally works. Okay. So there are some Numba tips that obviously, as we discussed, that now the best performance we get from NumPy. If you only stick to NumPy arrays, it is okay speed increase for maybe tuples, string, and your types are scalar in float bools, like a Python in float bools, not NumPy. And it's quite bad if like suppose it does not know what's the length of that your object will be. So you don't know what the length of list and dictionary is. It is mutable all the time. And what if there are like classes you define? So it's also bad sometimes for classes. And so again, the warning is that only use if must required. Serial execution is definitely enough for most of the task. We can also merge them. We can also merge what are technically some multi-threading and number for your for your gains of performance. So I mean, this all theory, and we covered like mostly all the topics we should do. Now let's and put it into code, because this is more of a very hands-on topic, not like AI where you have maths and all. So there's a, I guess, a collab link shared by Vivek. Can on the group. You can see that, and meanwhile I will also run that code in my VS Code. Yeah. So if you
maybe increase the font by 1 or 2 levels.
Yeah. Yeah. Is the collab shared in the group?
Not shared. You want me to share it? Yes.
Yeah, I mean it would be.
Okay, I'll send it right here on chat. Okay, I'll send it.
Yeah. Okay. Is it better? Can you see my code now? Okay.
Yes. Better.
Okay. Yeah. So since we said that, I mean, this is very hands-on thing. There's not much math in this, so we will code on the side, and I made a notebook to where you can clearly see your performance gains and how you could speed up your code. So here I taken a basic example for this entire code. So I taken your basic Boston house pricing data set. Okay, and I had tried to train it using SVM. So why I use SVM? Because with SVM we know that it cannot be parallelized. Like there is no n jobs in SVM if you have ever used it. So there are some models in scikit-learn which can be parallelized, such as trees, because every tree is independent of every function of each other. So that's why they can be put on multi-thread multi-processing. But SVM and all others cannot by default. So here what we'll do is we would train a SVM model on our data set. And at the time of when you want to predict it, so at the time of predictions, you are only given like one core and one CPU to work with. What if you want to do billions of predictions at one time? So that time you want to put so let's get started. So, and obviously initial all the libraries, and this is downloading the data set of housing data set. I already have downloaded, so I won't. And this is just all the train function. So we're not interested in much in training. We are very interested in inference. So I just run all the training at once, where I defined a pipeline and everything. And yeah, so I prepared my final data set, just housing prepared train and housing prepared test. I will use SVR with kernel with a polynomial kernel and C as 100. So let's try svr.fit. So yeah, so our model is mostly trained now with SVR. As I talked that you don't have any njobs function here. If you see our random forest, you will find njob functions. So what happens is with random forest, if you give n jobs while training, it also takes m jobs while testing. It's like if you're given 8 cores while training, it will also try to use the same the 8 cores at the time predictions. So it's not much of an issue there regarding those models. It's issue when you have such kind of models where it can't be parallelized inherently. So so now let's try predictions. So we have fit our model. We have SVR REG, SVR REG model. So we try to predict this using our test data. So I'll just show you what my test data size is. Okay, sorry. Yeah, if you see my 1000 prepared test is 4128. So there are total 20,640 data points. We put 16,000 in train and 4128 in test. So I have 4128 4,000 data points. Now let's see for this 4,000 data points, what is the time it takes. Now, if you're aware with some magic functions in Jupyter, there are mostly two we will use. One is percent time and second is percent time it. Let's check if I just use percent time. So this percent, I mean this time would measure your whatever your next line that you're giving, or like for how much time it runs. So if you see here, wall time is what we're interested in. Wall time means the total time taken by the CPU entirely. So here for this instruction of dot predict, we took 863 ms, 863 millisecond. Now the difference between time and time it is that time only runs it for one time, and if you do time it runs for 7 times and gives you average of your time spent. So if I do time it will take more time, but it will give you an average of this 7 runs. This is very useful because sometimes what happens is when you use time, there might be one more code running in the background, like some song is running. So your CPU will also include that time. So it's better to use time it mostly. So as we are seeing, we are taking 815 milliseconds for your entire SVG predictions. Okay, and let me get this house prediction test. This is my predicted output. House prepared test, I got house prediction test. So now this house prediction test, if you remember, what that data set does.
So Shreyas, if folks are trying to run this in Colab, it won't run, huh?
No, it will run mostly. It should run. I didn't like explicitly test it, but it should run. Some functions may not run, but that is okay.
So you are running it on local Jupyter, huh?
Yeah, this is my local VS Code because I need to use like HTOP monitor here at the side to show you like what is being run in background. This I can't use on Colab. That's why.
Okay.
Yeah, so if you see, this is my data set. It had long. So the Boston house crossing data set is very famous, where you predict your median house value from 13 input features. Input features are where the house is located, longitude, latitude, median, range, and these are all the features. And you predict your house value in dollars mostly. Now I predicted my house value in dollars for my test. Now our task was, as we told, like since SVR can't be done on parallelly, it's only using one core, one thread. So let's try to use multi-processing for that. So how you introduce multi-processing? So there is this module in multi-processing called for introduce multi-processing called as concurrent dot futures import process pool executor. So this process pool executor is what nowadays and mostly the practice is used when you want to do multiprocessing with a context manager such as with. Now here I have 12 cores, so I'm
This
giving
is a Python package, process pool executor, or something to do with Numba?
Everything is fine. This is all everything Python. So I have currently
core
not started with
Python,
Numba.
okay.
Yeah, everything is core Python. I have not started with
Okay.
Numba yet at all. So our remember our first use case is trying to put this SVG predict on many cores, not just one core. That we try to do using Python first. So when I try to do using multiprocessing, where I'm using 12 cores and I am putting this svg.predict function on housing prepared test. So what is happening is it will take 12 instance from your housing prepared test and try to put all the 12 together on all the 12 cores to this function. Now if I do this, let me use time it. So x.map it, so it kind of maps your this function on this thing. So if you see, it's actually much slower, 7.5 seconds as compared to 815 milliseconds. So this is kind of, surprising. Now, why this is happening? Because scikit-learn, if you go to this link, scikit-learn by default does not behave well with your multiprocessing module in Python. If you open that link, so authors of scikit-learn say that. So if you have earlier used scikit-learn, there used to be a package called as joblib, which was within scikit-learn.external package. So if you open this from sklearn.externals import joblib. So this joblib was a package made by scikit-learn team back in 2016-17. Nowadays they made it as a very independent package. So this joblib is what handles your and jobs equal to -1 equal to 8 in the background for your any ML task, and hence it does not play well with your any Pythonic based multiprocessing module. So we will use joblib here. Why try to do the same thing? Why try to make it parallel? So, but nowadays it has moved from external to a separate package. So that's why we already imported a joblib above. To use a joblib, I use a module in that called as joblib.parallel. And there are two important things is in this module. One is parallel function and one other called as delayed function. So we'll see what this parallel and delayed do. Yeah, so now I'm using this parallel function which I used earlier. Okay. With parallel, now here I get to define my number of jobs. So this parallel, what to do is, so you have to call your function as we have to predict within this parallel. So you first define your parallel function and n jobs equal to 12. Now here I gave here prefer equal to process. So this process means I am trying to use multi-processing, not multi-threading. Because internally SVM is very complex, and it would definitely slow down if we use multi-threading. So we use multi-processing here. And I say that delay. So delay means since multiprocessing is there's a one key issue with scikit-learn that you want like one process to execute some fraction of time later than next process. So this kind of how internally the joblib works. So if you open this link for joblib, you will see why they use process and these things. So if you embed paralleling for this, you read this blog post. So they talk about why they use delayed and all. So I'm putting my this earlier function svr-ret.predict and giving it input housing prepared test. Now instead of passing all complete housing prepared all like my entire array at one time, I'm putting it in a for loop. Like for I in housing prepared test, I'm giving it I.reshape. So reshape is because your like this housing prepared test shape is 4128.13. When I do every individual component, I'm passing it to give me shape as just 13 comma, which we don't want. We want 1 comma 13. Because it's one instance and 13. So that's why I used .reshape 1 comma -1 here when you give it. Now let's check what we get. I'll just time it. And let's see, since I'm using multi-threading here, multi-processing here, it should use all my cores. Now, if you see, this is a system monitor called as htop. You could, maybe if you use Linux, you could install this htop and see how it does. On Windows, you have Task Manager. On Task Manager, you can see what is running. So above the 12 that you're seeing, this 12 are my cores. Above this 12 are my cores, and this memory, like this is my RAM currently being used. Currently, I'm using 9.8 GB of 16 GB, and I have 12 cores. And and this is a process. So currently, my 121% is used by Chrome, which is I'm currently showing you on the.
So
Chrome.
you're saying that if we run this in Windows locally, we have to check Task Manager.
It's like if you want to observe like what is actually happening in multiprocessing, like we are trying to use 12 cores, right? So it should show that all my 12 cores are being used. So if I run this, it will maybe show you. So
you are using Ubuntu, so you are using htop, which is Ubuntu thing. Okay.
Yeah, on Windows you can use Task Manager. It would be okay. So if I run this code, if you see now all my cores are being used, all the 12 cores are being used 70 to 100%. If you see all that, and it finished also very quickly. So I use 460 millisecond now, as compared to earlier, I had to use almost 860. So if you see, we have almost half the time for svg.predict function by using joblib.parallel here. So you can use this in your task where like you have like currently I had only 4,000 to test, it's fine. But what if like if I'm serving this as a web page and every time a user is inputting one thing and I had to predict it in the batch. So when you have to do batch predictions with millions of computation with millions of input parameters, definitely we could have used this for only those algorithms which cannot be parallelized by default, such as SVR and obviously SVR. So for one thing, so definitely as we saw, so we got twice as good as speedup. So now let's introduce some overhead on our function. So we had just trained our model, we had just predicted it. Now let's do some computation on the prediction, because that's what maybe you're like in real world code, you will just not do prediction, you will have to do a lot of post processing on the predictions. And that might be heavier than the prediction itself. So what I'm doing is I just created my own custom function that these two functions, future wealth and compute median. So I got a house price right now of a house in Boston. I am saying it, I am just trying to predict what will be his house price tomorrow, like one day later. Okay. I do that by just using this one more function. So this is my house price for the next day. And so if I input the current day price here, it will multiply with these two constant R and S plus W. So I kind of made it a Y equal to MX plus C form, where your R is randomly initialized currently NP dot where randomly initialized from e raised to power X V1. So V1 I just given some constant V1 and V2 plus some random numbers. Now this random can be anything, like for every, so we don't know like tomorrow what will the price of houses. Okay. So for example, I just say that R is kind of gross rate of return, S is savings rate of the household, Y is income of everyone in the household, then tomorrow the price of the house will be this. So this is the future function. And one more function is now suppose I had like 4128 houses, right? I want to predict for all the 4128 houses at the same time what will be their prices, for example, after 2 years, 3 years. So for all the 1,000 houses, maybe like after 1,000 days, what will be its price, and I compute the median of those all the houses. So what is happening is in our Boston house pricing, we were able to predict for one house what will be its price, what will be its price given all the input features. Now I'm saying that for an area of 4,000 houses, what will be its price after 1 year? Okay, so that kind of function is computing median of all the prices of all the houses in that area post 1 year. So 1 year, I mean I said 1 year, but I'm saying like here instead 1,000 days. So now this function is fairly heavy because we are trying to compute like we are also calling this function, we will compute the next day price. And on the next day price, we are doing it 1,000 times. So we are using running 1,000 loops, like 1,000 loops inside one more loop where we're already running for 4,000 times. So this number of so since we are doing it for 4,000 houses, my outer loop runs for 4,000 times, and my loop inside runs for 1,000 days. So the total computation here that I had to do is fairly high, like 4128 into 1,000 goes to 4 million computations for this one loop, almost. So let's see what is the computation time we will take with normal Python. So this is just a graph. Oh, sorry, I didn't define this function. So just for one house, like today it's 17,500. Tomorrow after 1 year, maybe the price is going down for just one house. So we want to do it for 4,000 houses. So let us spread it. So here I'm doing twice percent in time. So if you do twice as percentage, it will compute it for complete block, not just for like one line. So if I'm doing percent time both, so let me compute median for all the input houses, like 4,000 input houses, and let's say how much time it takes. So this should run, I mean, for 11.9 seconds. Sometimes it gives me 12 seconds. And also it ran for 11.9 seconds. Fine, we'll try it one more time. Yeah, so the entire computation got finished in 12.2 seconds, which is obviously fairly high. If you are running this on web prediction, you cannot wait 12 seconds for prediction. For your computation on top of prediction. So what to do here? So this is a final value 1.84. Don't get confused with this. This is a return value from np.median. This is the median value of house. Yeah, so it's 12.2 seconds. Now, so to get started with any kind of multiprocessing, multi-threading, Numba, you first have to know your code as like where the bottleneck of the code is. So that's why there is something called as code profiling, where you profile your code and analyze what is the issue there. So I shared a link. You can go through like how the profiling is done. So, but here basically we'll use one magic function called as prun. So it profiles your run or whatever code you're for whatever function you're using. So here I'm profiling my compute median, and let's see the code. So why I'm doing this, because I want to know which line in the code is causing this 12 second, like where the compute time is spent the most. This will take same time as like 12 seconds to run. So if you see here, like 3 columns here, and the right side, if you are the actual name of the functions. So we are introducing something called as come time, which is cumulative time. So here it took 13 seconds for this function, future wealth we are seeing, and it took 14 seconds for something else. So this 14 seconds is total for compute median. Within that 13 seconds, it took only for future wealth. That is here the earlier function, because we are calling here, right, within loop other loop. So now we'll see like within like if I want to check for this future wealth. Now as I see that future wealth is causing some issues, now I'll copy that future wealth and run it using one more profiler function called as line per run. So this we did for function prun. There's something called as line prun with a function I pass it called as future wealth function within this compute medium. Now when I try to profile this, I will get to see line by line as to where the issue is. So again, it will run for maybe 12 seconds. Yeah, so now it gives you such output where on the right side you have your code. On the left side, you have like for that each line, how much time was taken. Now this time is not actually seconds, 43.35 seconds. It is just like relative computation time. But here we see the maximum time was spent on this like this getting the parameters from NumPy, and so that's one good to know. Like most of the time is spent there. And one more thing, let's also profile your the function itself, the compute median. So when you do multi-threading, you will get to know that which line that you actually care about and where you want to do it.
So Shreyas, you had added purposely those complex formulas, right? The exponential
Yeah.
V1 into rand and into 1R. So there to inspect how this optimization will work. Otherwise, those formulas didn't have any other basis, right?
Yeah. Actually, I just wanted some future for future house price, so I just gave some random values.
Okay, some random formulas you came up. So check
the
optimization. Okay.
Yeah. So as I think it's totally taking 12 seconds. So I mean, it's a heavy optimization. And same thing. So when I try to profile my compute median function, I'm getting all the code here, and you can see here 91.9% of time is spent only on this line, future wealth. So what this has given you is maybe if you're trying to spend time on some other functions, it would not have been much beneficial as compared to if you spend time only on this. So get to know that now. So so this is just a brief overview on profiling. This is a very brief overview. There are many tools in profiling that you could use. This is just a very brief overview. So now we know 91.9% time is spent on this future wealth. Now let's try to use Numba and try to speed up this. So with
No, but what about that multiprocessor of Python itself, concurrent something you were trying before?
I could do that multiprocessing, but right now I could, but I want to do that along with number.
Okay, got it.
Yeah. So I would like speed up individual functions using number and then use multiprocessing on those. So that will give us much faster, and we'll see what the difference is. Okay. Yeah, there's a good point that we talked about multi-threading, multiprocessing. I could try this here, but let's first optimize individual functions and then use multi-threading on those functions. So so now getting started with number. So the key idea is to compile functions to native machine code on the fly. So which is also called as just-in-time compilation. Like we are not explicitly compiling one step after time, like not in two steps. We are doing it at the fly, on the fly. So there is something called as JIT for that. So we from number we import JIT. Now if you go to the number site, there's an example they have given. Sorry, let me Google. Number.pydata.org. So there is example if you see on the website where they have given for Monte Carlo, where you get the value of pi. Try to get the value of pi using Monte Carlo tree search, not tree search, just normal Monte Carlo. So what they have done is, so let's try to use the same example here and try to use JIT on that. So first let's use the normal function what they have used, Monte Carlo pi, and let's check the time it takes for 1000 iterations. So it is taking wall time 3.3 millisecond. Now if I JIT this, so how you can JIT a number function is something a concept in Python called as decorators, where you are calling your function within another function. So that is kind of use of decorators here. Now you can also use decorators if you have seen it earlier by using something called as @ at the top of function that you want to use. Something like this. This thing is same as exactly as this thing, but what is happening is your Monte Carlo, when you call Monte Carlo, it is for executing the code in itself and then passing this code through the JIT, and the output we are getting is via the JIT function. So that's what is happening. So I define here Monte Carlo pi JIT, a new function where it is Monte Carlo pi when passed through JIT function.
No, sorry, come again. What is JIT doing again? Just-in-time compilation.
Yeah, so as we discussed earlier in our PPT, let me open. Yeah, so what number does it compiles every function individually. It doesn't compile your whole code together. So when you pass it a function block, it will compile it. Compile it means it will convert your function block into machine code that will be able to run very quickly when you at runtime. Just that. So it will be able to take whatever function you pass in. It will analyze that function, convert it into machine code, pass it to lower level functions, convert it to machine code, and then it will run it very quickly. So they call it as just-in-time compilation, as compared to normal your two-step compilation, where like in C, where you first run in C, what to happen is you first compile your code first in first step and then run it. That is two-step. This is what they call just-in-time, where you do it on the fly, like at the same time your code is running.
No, but Python is normally interpreted in real time, no?
Yeah, Python is real time. That's what. So Python is a language which is definitely done in real time, but it is not compiled in real time. So what is happening is it is using compiler to convert it into a bytecode, and then it is passing it line by line into PVM. Here, like why are you able to use list? Even if you don't know your like what the size of list is, we're still okay because it's not completely compiling it because it is executing line by line. With number, what is doing it knows all the size of your function. It it gives them all the space in memory before you execute the code, kind of they call it at the runtime. So it gives all the space to the code before running, and when you run it, definitely it's faster because it's already given the space to variables and all. So that is the difference between your number and versus your Python. It will be more clear with an example. Like if I try with normal, as we see, so I'm using JIT on this function, okay, and created a new function called as Monte Carlo Pi JIT. Okay, now with normal function when I try to execute, we've got 3.3 millisecond. Now let's try using this Monte Carlo JIT. Okay, so now issue you're seeing that it's with using number, it's actually higher than your 3.3, almost like 100 times higher. Now why is that? So so we discussed that number does something called as compilation of the function before, and that compilation happens first time. Like when you are running this function first time, it first compiles the function, like sees all your variables, like it is seeing x, it is seeing y, it is seeing acc, and then assigning them space in the memory, and then making a run for it. So when you write first time, it does all of that. So when you run any number function first time, it will always be higher because it is also compiling as well as running. Now when you run it next time, so I run it once, now let me run it again. You see how fast it is, 90.8 microsecond as compared to 3.3 millisecond. Because first time it compiled and ran, now it just ran it, because now it has compiled, it has given the space in the memory. Now this x and y is stored in my memory. In my memory, it will always be this and all. So that's why it's much faster when you do it next time. Okay, so that's why mainly people use time it, because time only runs once. When you use time it will run for 7 times. So it will give you average of all the 7 runs, and it will definitely be faster. Yeah, so it's 90.2 millisecond for average run. Yeah, so now let's come back to our original function. So our original issue was when we tried to do compute median, it took us 17 seconds, 12 seconds and all. So let's try to JIT it. Okay. So I computed, I'm doing the same thing what I did for Monte Carlo. And but before this, let me ask if anyone has a doubt, because going forward it will be even more complex. So if I understood JIT, like what we're doing here, if there is anything, I guess it should be clear.
So JIT is one of the facilities in Numba. Is
Yeah.
that right? So there are other things Numba provides.
Yes, correct.
Okay.
So from Numba, we are calling that just-in-time compiler, and we are passing your function to that just-in-time compiler. Just that we're doing, nothing else right now. So is that okay?
Yeah.
Yeah. So again, going back to our original problem, we had to run this this code for 12 seconds. So let me JIT this. So I created a JIT function, and now I'm computing the time to run this JIT, where I give input as my house prediction test and running this function which is JITted now. Okay, now it is giving some warning, but it's still running. We'll see what that warning and what it means. Yeah, so it again ran higher. It's again weird issue. So it ran for 12.8 seconds as compared to we're able to run 12.2 seconds without JIT. So with Numba, actually, it's actually much better to know like what errors you can run into as compared to what are the best practices is. So I purposely did an error that, so we have to go back to the warning. Why is it happening first? So the warning, if you see, it is that cannot determine number type of class function. Because we had already, like we are using one more function inside this, right? If you go back to the function, compute median. So it is trying to analyze every variable, and it cannot analyze this future wealth function because it has no type. It's just a type of object. It's just object of type function, and this is also not made into JIT. So that's why it's not, since Numba is not able to optimize this, it will fall back to something called as object mode, where instead of converting your variables into very optimized thing, it is converted into objects, which are kind of same as Python objects. So if you read this, it's running object mode. So this happens mostly if you are calling one more function which is not jitted, or what if like number is not compatible with types in it, such as list and all. So so what happens is it's not actually good practice to get this warning. So instead, we just try to not get this warning at all. So we use something called as no Python mode equal to true in the JIT function. So like I don't want to run this in Python mode. I want to run it only the compiled version, not only the optimized version. So if you do computed no Python true and try to run it again, this time it won't run. It will just throw an error that since we said that we don't want to run in no Python mode, it will just throw an error that there's issue at function name. This is what we want all the time. So so that's why we use JIT with no Python equal to true, and the short form of that is njit. So from number, if you import njit, it's kind of no Python for JIT, just that. So from here on, we'll always use njit, not just use normal JIT. Now let's try to fix this. So when you try to fix this function, so fix one issue was this feature was not made into JIT. So I made this into a JIT itself by using a decorator at the top, and this was the original function. Sorry, it will be helpful. So this was our original function where again I'm just going through it. You have number of number of iterations, and your observation, we made a list. Total list, and then we're appending to that list and finally getting the median. So now I have made both into a JIT. Now this should be run, I guess. So I made them into JIT. Now since I made them into JIT already, I don't need to call the function and create a new name for it. So like earlier, what we did was we created a new function JIT, new function compute medium underscore JIT by calling this function on the JIT. But since we are already giving that this is @, so we don't need that. Now when I try to do it, let's check. How much time it is taking. Okay, it's still taking 12.1 second. There's again one more issue here that so what is happening is we have OBS as list, and we are appending to that list, and finally we are computing numpy.median on that list. Now here obviously internally what happens is Python takes care of this, where it will internally convert your list into directly assigning your list object into a numpy to create a different list, different numpy array from that list, and input median on that. But this is not clear to Numba. Numba is seeing this as different two data types within one variable. So we had to explicitly do it as numpy.median for numpy.array. So we explicitly convert it into numpy array first, and then do numpy.median. Now this should be our completely optimized function. Now it is running for 12.1 second. Now it is first compiling. .6. Now let me rerun it, because first time is compiled, second time is getting it faster. Okay, it ran for 11.6 second. Yeah, also it ran for a bit faster. Actually, it should have been in millisecond. Let me check. Yeah, I guess because we are again defining this as list here. So we'll see how can we even make this faster. It went from 12.2 seconds to slower, but it did not affect much. So we'll see later. Yeah, 12 seconds. So let me do this with list if I try it, where I input gave it as list instead of a normal Python numpy array. This will also cause an issue. It's something called as a reflection problem number, because it's again there is no computation increase, because when you're passing it list, it cannot figure out like what's the length of list is. So always better to pass a numpy array to it instead of list. Yeah, so let's optimize this function what we already have by making some changes which are asked by number to do. So earlier we were, for computing this length, we are calling the length function. Instead of calling the length function, let's just use size, numpy size. Instead of using list, let's just pre-allocate this list with numpy.empty. And instead of using append, we will just append a new value into the numpy array, and we're outputting it median. Now, since this OBS is already a numpy array, this should be fine. So we gave it new names: future wealth NP and compute median NP.
So Shreyas,
Yeah.
sorry to interrupt. So all of this is happening at training time or inference time, or either?
This is all at inference time. Our training is done long back. We just got predictions for our houses. So our problem was, once you get prediction from the houses, we are doing further computation on that predictions using compute median and future wealth.
No, so you're saying all of this is being done at inference time?
Yeah. So assume
Okay.
that you have this function at time of inference that you want to run. You can't wait 12 seconds, right, for any inference to happen.
So training is not addressed because that's not an issue either.
Yeah, training is done once, so it doesn't matter.
Okay.
Yeah. So with training, we got that right. We tried to parallelize the prediction over multiple cores using joblib. That was one thing. And then now we are doing post processing on this. So post processing on the predictions. So that's why I defined these two functions, which takes some more time to do. Now what I done is I optimize those function. Instead of like using length of length of the list, I'm using just size directly, so it doesn't have to call length function. I converted it into numpy array, so I like pre-allocated the size and just appending it and computing the median. So let's run this, our new function. Let's benchmark this with our earlier implementation. This should be faster than by 0.6 seconds than the original. Like almost by 0.6 or something. Okay, I mean it's a bit faster, but you won't see much speed up increase, because as we said, our maximum time is being spent on this function here. We optimize the parts other than this line, so maybe it won't affect much. But going further, you would know that instead of using list, you just pre-allocate them. So let's try to inject this. So I'll remove this argument for now and just use simple inject. Yeah, so we are again injecting this. I'm renaming them future wealth NP inject. Now let's compute this NP inject and how much time. So it should take 499 millisecond. If you see, it is much better than 12.1 second that we had earlier. Is not defined. Okay, oh, NZ is not defined. Okay. From number. Yeah, so if you see the drastic difference, when I change some function where I remove list and just use numpy arrays here, there is no list here. It has done speed up from like 12.1 second to 492 millisecond. Now this can be deployed feasibly on a suppose web service where on predictions, if you want to do this. So this is the speed up of number. Now this is just using one thread, one CPU. There's no multiprocessing, nothing done here. Just the power of your just seeing compiled function of number. Okay, so you got 492 milliseconds. So what we'll do is, you want to go even faster than this. So we would try multi-threading with number, as we discussed earlier with multi-threading. You could use multiple threads to define your code. So Here I'm using thread pool executor from concurrent.features. This is an inbuilt Python method. And I'm computing this function, which is my numpy and jitted function already, and passing it house predictions test, which we also are doing till now. Everywhere we are passing this input. Now let's check what the speed up that we get here, or anything, if at all. So it ran. This is weird because when you use multiple threads, it should go faster, but it has actually run slower, 903 milliseconds. This is because, if you remember the presentation, because of GIL. So there is global interpreter lock on threads, where Python can only execute one thread at a time in the end because all our other objects are locked. So there's something called as where to open this GIL. So there's a lock where to open that lock. That lock can be opened using Numba itself. So within Numba, there's a function. There's an argument, like instead of this ngit, if you give ngit for no GIL equal to true. Now this fast math is another argument where it's just good. It's a good practice to use fast math argument. Will just try to vectorize your operations, whatever mathematical operations are trying to do. Like I'm trying to do here sum and star. So it will try to use fastmath library. So this fastmath interacts with Intel's MKL library in the backend and try to speed up your math operations. So this is by default a good thing to use fastmath every time. And here main thing of interest is no GIL equal to true. So we are instructing the Python compiler that to open this GIL lock GIL at time of execution. Same thing I would do for both functions. So no GIL equal to true, no GIL equal to true for both. Again, rerun this. So now let's try with while releasing this lock, if there is any speed up that you get. There it was 100 milliseconds. Now I release the locks. Here my process. Okay, it's a bit faster, but not as much as we would like it. It's still slower than individual Numba thing. So why is it happening is because our threads are not independent here. Because if you see here, W equal to W01, and there's also one more W inside the another function. So this W and this W are kind of same, which are being shared between different threads. So they are not like being able to use power of multiple threads here. So that thing you will have to be know. And one thing we talked about multi-threading was it's mostly very useful when you have input-output types kind of operations. So here our code is not input-output heavy. We are bound by CPU. We're not bound by input-output. Suppose every time I had to import a file and output a file, then maybe processing threading would have been faster. Here I'm just bound by CPU, and there's no input and output here. That's why maybe the process spool should work faster. Process spool as in our multiprocessing module. Okay, so now let me try using this multiprocessing on our function. So this is again, so this is everything with Numba. So this is threading with Numba, and this is multiprocessing with Numba. Where process pool executor for 12 cores. Now if you see, all my 12 cores are being used here somewhat. And it if you see this home.shreya, so when you run in Anaconda, where is my process name? So since we're running from Anaconda model, the path should be towards an Anaconda thing. Okay, it's not able to show on process here. But okay, now that's just completed. Okay, now just surprising, it took 2.54 seconds. This is much slower than just individual Numba itself. This is again why, because we are not able to parallelize these loops in itself. So we are able to parallelize just using Python. If I hadn't used maybe Numba here, it would have been faster by default using multiprocess. But since I'm using Numba, this function is already compiled. and it's not able to use these ranges effectively. That's kind of a thing. So what is happening is there's inherent paralleling in Numba that you could use instead of using Python's multiprocessing module. We'll check that out. So what I've done here is added one flag called as parallel equal to true. So this parallel equal to true, what it does is there is inherent multiprocessing inbuilt into our Numba functions, which you can invoke using this parallel equal to true functions. And there's one more change you could do is I import something called as p range. So instead of using normal range in for loops, you could use parallel range here, p range parallel range of Numba, where it would automatically put your every iteration of the loop on every core. And make sure to only use this p range where you're sure that all the computation inside the loop are independent of each other. What I mean by that is I'm using p range in the outside the loop, not in the loop inside it. Why? Because all the computation within this, so this computation is independent of I plus 1, but the computation within here is not independent of I plus 1. This W is dependent on its previous value in the loop. So cannot use p range here, it will slow it. I can use p range in the outside where everything is independent. So let's try again. I'm making it a new function, compute median numpy jet parallel. Now let's try to run this. As you can see, it's a spoiler, but now we're doing inherently multi-parallel. So if you see the spike, it should spike all my cores at same time for some very small amount of time on the right side. Yeah, see, all went to 100%. Okay, all of the cores. And the speed up that we got finally, after doing all of this using multi-threading, multi-processing, using joblib, using parallelization, converting list to NumPy, vectorizing your NumPy, we got final loop time of 67.3 millisecond, which is much better than our 12 second earlier. So roughly the computation, the speed up that we achieved is 200 times using NumPy and multiprocessing module. So that is my kind of mic drop moment, that we could achieve 200 times speed up here. And this is only for 4,000 input, right? What if, so this, as you heard in ON and ON complexity, as your input size increases, your computation time would increase. Here, even if I increase from 4,000 houses to suppose 10,000, my Numba implementation would remain still the same, but normal implementation would increase. Like if I use 4,000 to 50,000, it would, instead of using 12 seconds, it will use 50 seconds, but this would still run at 67.3 milliseconds because we had used Numba and parallelized the function and everything. So that's the major thing. So that would obviously increase as your compute size increases. It would your speed up, your fraction of speed that you're getting will also increase exponentially from 200 to maybe 400,000x. So that's the takeaway here for Numba. You can refer the notebook further going forward if you want to implement it yourself. And that is it with our Numba implementation. And I think I covered everything here. So yeah, if anything doubts or something, or should I move on to a new topic, which is the Rapids? Yeah. Yeah, I mean, this is more hands-on. I think you have to do like actually run the code to see what is happening and what is not, and how we can do it.
Yeah, this reminds me of code profiling on Java and C++ we used to do before.
Yeah, exactly that. Yeah.
So there were some tools, I think LoadRunner or some other tools were there. Java profiler for code profiling. So there also we were trying to optimize its performance.
Yeah, so we did all of this because it's possible. Like in deep learning, you have GPUs, so it's not much of an issue there. Directly use GPU, but with machine learning, you don't. And just with normal Python, you can't use GPUs directly. You can use, but it involves a lot of overheads. Like you have to write your own threads for GPU. You have to write your own kernel. This is a much easier and much faster solution than going into that space. And for this bound tasks which are on CPU, so we could achieve it 200 times just using CPU. So that's why it's very useful. And if you want to deploy this ML model on a Lambda service, you could do this. because it's now taking inference time of like this millisecond as compared to seconds earlier.
So this code will deploy on the cloud?
Yeah, you can.
Like AWS Lambda or SageMaker?
Yeah, you can able to. I mean, you have to
And
install them.
it will work as per the optimization logic?
Yes, definitely. It works on Colab, so definitely work on there. Yeah.
So another question, what about neural networks, Shreyas?
Yeah, so neural networks, see, the libraries that we use for neural network, PyTorch and TensorFlow, they're already using optimized C++ at the backend on CUDA, on GPU, at inference time.
So they don't need optimization.
They need optimization. They need optimization in terms of their networks, parameter size, and all, not in terms of pure computation on hardware. They are already multi-process, multi-threaded, everything.
So you won't apply Numba on deep learning code?
No, and it's not even needed. Why should I? Like, it's already multi-thread, already multi-process in TensorFlow and PyTorch. If you like on the GPU, what difference is on CPU? I'm already given 48 cores. On GPU, you have millions of cores, like in thousands of cores.
Now, if I'm running TensorFlow PyTorch on CPU, but then also TensorFlow and PyTorch will optimize it.
Yeah, that also, yeah. If you suppose if you do PyTorch.autograd, that is already multi-threaded and multi-process inherently. We are talking about just Python here. With ML inference is mostly everything is done Python. Anytime, any code that you see, everything is Python. We are not using PyTorch for ML inference anytime.
Okay,
Like
sounds good.
scikit-learn or random forest, there is no TensorFlow or PyTorch used there. We are just using Python. So we have to figure out a way to multiprocess our Python code manually. So that's where the Numba in this comes in. If you have PyTorch, then it's no issue there. Just use PyTorch every time.
Got it.
Yeah. So that's the use case. I mean, that's the particular use case which I want to target, which are faced in my work and everywhere. Yeah. So this mostly use case you'll find in scientific computing, where like suppose you want to do physics kind of based simulations in Python. There you can do PyTorch because it's just mostly SciPy. So it's also very useful for SciPy, where if you want to parallelize SciPy and, for example, stats models and all that, so it's very useful there. So yeah, so moving on from our Numba to Rapids AI. This is just a very brief, I would say, introduction to Rapids. So Rapids is nothing. So what happened was the problem that we are talking about ML not being on GPU. This NVIDIA saw as a use case and flouted their own libraries called under a one umbrella called as Rapids.ai, where they made something called as three libraries within them: cuDF, QML, and QGraph. Where cuDF is nothing, just pandas on GPUs. QML is nothing, scikit-learn on GPUs. All the functions are exactly same, although the newer methods are algorithms are still getting added day by day as we see. And QGraph is one more, which is used for graph computation. Now this cuDF, QML, and all these three are completely in Python. There is no need to go into C++. So they have made an interface between Python and CUDA API using this cuDF and QML. Kind of. So and all the other things that you see, Apache, Dask, where they say that they are using distributed computing on GPUs across various GPUs. They're nothing. They're just using cuDF and QML on their backend. Even like H2O.ai, the AutoML framework, they say they could compute XGBoost and many algorithms on GPU. That means that they're just using QML in their backend somewhere. And if you want to do it yourself, you can do it yourself also. So this cuDF, go to the next slide. Yeah, so this is what they define a new data science pipeline where you could put everything on the GPU. And at the very bottom, it uses Apache Arrow as to do it on GPU memory. It is their own thing. So cuDF for analytics, QML for machine learning, deep learning, we know everything is in deep learning. Yeah, so let's just do two examples for cuDF. Yeah, so cuDF is based is a data frame library for loading, joining, aggregating all your functions for manipulating data. It's exactly same as pandas. Almost like all the functions on pandas are like implemented in cuDF. So it's always easier. So what if like at the time of predictions you are loading a data frame? So that time, just using normal pandas, use QDF. So if you're loading, suppose 100,000 lines of data frame, that loading time is actually like 2 seconds. In pandas, if you use QDF, it is 0.1 second kind of. So it will obviously help in inferencing as well as during train time if you are training using QDF. So just one example here I'm showing you where the guy is read CSV using QDF. So you import QDF and just read CSV normally, and you can use all the functions of QDF, group, byte, mean, and everything that is defined in pandas. And then next is QML. So QML is same. They try to copy like sklearn's methods, all the functions within sklearn. So with QML, suppose you want to implement SVM that we did right now, you could use SVM GPU instead of normal SVM. And if you use time it for training, so with sklearn you could train only on CPU cores. Even if you give it n jobs, it will able to only use CPU cores, not GPU cores. If you use GPU here, SVC GPU, which is on QML, it will be able to train on GPU. So the timing is almost half on the right side of the graph. I just borrowed from online. That on sklearn he was able to do it in 48 seconds, and on QML he was able to do it in 20 seconds. Training faster, so it's like half as fast. So it's the use case for QML mostly is like when you have very large data set size and you want to do ML on that. Mostly, obviously, people use deep learning when you have a large data set, but in finance domain and all, you can't use deep learning. So this you could use QML on very large data set, which will speed up your training time by a lot. So yeah, I guess that's it. And this is just a brief introduction to Rapids. Maybe if I get time next session, we could do hands-on on Rapids. But yeah, for now, this is it. So Numba and QML. So let's recap. We started with why we need parallelization and for the code. And then in the code, what we did was we tried to parallelize the dot predicate function of sklearn. We put it on multi GPUs. We saw it was twice as fast than normal predict using joblib. And then we tried to profile the code. We saw various tools for code profiling for Python, and then we see that in which line we were able to face the issues. Then we started with Numba, and then we saw with Numba that we could use JIT, just-in-time compiler, and sometimes although you have to use NJIT, no Python mode. What if like Numba fails to compile, then it falls back to no object mode, which we don't want. So we use NJIT all the time. And with NJIT, with Numba, you have to take care of list, not use list, and like mostly use different data types and try to pre-allocate your memory. So we converted our function into all NumPy arrays, and that gave us 10 times speed up, like from 12.3 seconds to we were down to 500 milliseconds. And then we tried multi-threading and multiprocessing. With Numba, we saw what were the issues with multi-threading. We had to reduce GIL lock. It made it faster, but it was still slower than original because objects were being shared. Then we saw multiprocessing, and with multiprocessing, it was said that it's much better to use Numba's own parallel module, Numba's own multiprocessing than Python's multiprocessing. There, finally, we were able to reduce it to 63 milliseconds, which is almost 200 times speed up. And we said that this would again be much faster if you have much greater input data points than like 4,000 to suppose millions of data points. It would still be the same, but your single thread would increase. So that why we are getting computation gain will always increase with your number of data points. And finally, we just saw introduction to Rapids and where we could use it. And yeah, thank you.
Okay, so thanks, Shreyas. Very nice session. Audience, any final questions? By the way, this Darshan Ganji, who's also a hardware expert with NVIDIA and other stacks, he has presented Rapids ML session, I think, one time.
Okay.
So we have another webinar in the Prime video list on Rapids ML, where Darshan had shown some code demos on Who DNN. So it's overlapping with that kind of sector, right? Accelerated computing.
Yeah, but for machine learning, not for deep learning at all. Yeah.
Right. So Numba is about ML. Okay, audience, any questions? Okay, so thanks a lot, Shreyas. A very interesting session, and learned something new here on ML optimization using Numba and just-in-time concept. So thank you very much. So look forward to your next presentation, Shreyas. And with that, we come to the end of this session. Thank you all for joining.
Yeah, thank you all.